Hi everyone. In this video I'm going to go over a way of solving systems of linear equations called Cramer's rule. So to use this method you want to be comfortable with determinants because it is an application of determinants. And instead of writing the notes as I talk, like I usually do here, I already have the notes written and I'm just going to talk about what's written. So let's say you have a system of equations. Okay, you have matrix A, and you have a vector b, and you have this equation ax equals b. Okay, so typical matrix equation system of linear equations. And so we can take the system, create an augmented matrix, bring it to row echelon form, and then solve it in the most common way, right? So the bottom row here tells us 10x2 equals negative 3, which tells us x2 is negative 3 over 10. And the top row right here tells us that x1 minus 2x2 equals 2. Rearranging and plugging in, so instead of x2, we actually put in x2 is negative 3 over 10 right here. And then we rearrange and we solve for x1, and we get x1 is 7 over 5 right here. So then we have our solution, right? Vector x solving this equation here, right? Vector x is 14 out of 10 and negative 3 out of 10. And here I just have 14 out of 10 instead of 7 out of 5 to keep that same denominator. Okay, alternatively, we can bring this to reduced row echelon form instead of just row echelon form, right? So rather than leaving the matrix in this form, we keep on finding an augmented matrix, bring it to reduced row echelon form, and of course we get the same answer, right? X is 7 out of 5 and negative 3 out of 10. Okay. Another thing we can do is use the inverse of A, right? So same matrix A here, same vector B, same equation we want to solve, and using the matrix inverse, assuming that inverse exists, we can actually rearrange our equation to look like this. Okay, by multiplying by A inverse from the left on both sides, we get the identity matrix here. And as a result, because multiplying this vector by the identity matrix doesn't change anything, we get vector x equals A inverse times B. So we can find A inverse by creating this augmented matrix where we have the identity matrix on the right side. We work with it to bring it to reduced row echelon form on the left side, and then whatever's left here is going to be the inverse of A. Right? So there is A inverse. Right? We can write it this way. We can also write it this way, which is a little bit easier. And then, as per this equation here, we multiply B by A inverse right here, and that will give us our vector x. We go through that matrix multiplication, and of course we get the same answer at the end. Okay, so here's another way to solve a system of linear equations, and this is called Cramer's rule. Okay, so given a matrix A and vector B, where A is an n by n matrix, and the determinant of A does not equal 0. Now remember what that means. If the determinant does not equal 0, it means A inverse exists. Okay, A inverse exists. So the determinant does not equal 0, A inverse exists, and B has n components, right? So the dimensions all match up. We can define a matrix Ni. Okay, so matrix Ni, it's like matrix A, except the ith column is replaced by vector B. Okay, so it's like matrix A, but the ith column here, that's why it depends on I. The ith column, it's if the ith column of A was replaced by vector B. That's what matrix Ni is. Okay, so for example, if A is 1, negative 2, 3, 4, and B is 2, 3, okay, then N1 will look like this. It's just like A, but the first column is replaced by B. N2 will look like this. It's just like A, except the second column is replaced by B. Okay, So that's how we define matrix Ni. Then, in this equation, Ax equals b, okay, xi, right, so the ith component of vector x here, it's equal to the determinant of Ni divided by the determinant of A. Okay, and so you can see why we have this condition that the determinant of A cannot equal 0, right? Because we're dividing by it. And that's also analogous to the condition that A inverse has to exist, which of course it must in order to solve the system of linear equations in this manner here. So, for example, okay, what will be the first component of x? x1 will be the determinant of n1 divided by the determinant of A. Okay, well there's our n1 right here, right? So we take that, find its determinant. There's the determinant of A down here, right? And what do we get as a result? When we calculate these determinants, divide one by the other, 14 out of 10, which is the same 7 out of 5, right? Because we solved this before, right? There's our 7 out of 5, right? Okay, so what do we get for the second component of x? Well, it's going to be the determinant of n2 divided by the determinant of A. We already know the determinant of A, it's 10, right? We calculated that before. So we just need the determinant of n2. There's our n2. Bring it down, find the determinant. We get negative 3 out of 10. So we, of course, have the same solution, right? 14 out of 10 or 7 out of 5 and negative 3 out of 10, right? Just like we have up here and the other times that we solved this, right?